All right, guys, welcome back to Introductory Physics Day 9. We are rolling through this, which is pretty exciting. We're already a third of the way done the course. So, woohoo, good job, guys, for hanging in there. Today, we are moving on to a new topic. Last week, we wrapped up our talk about motion in 1, 2, and 3 dimensions. We didn't really talk about 3 dimensions, but it's basically, just an extension of 2 dimensions, just like 2 dimensions was an extension of 1 dimension. And we're kind of done with that topic now. So this is a completely separate topic. Chapter 4, Newton's laws of motion. So chapter 4 and 5 are the main topic for this week. If we get through that, we'll continue to move on, of course. But our goal for this week is to understand Newton's laws and how to apply them in different scenarios. So hopefully today will be a review of stuff that you've already seen before. At least here in America, you tend to learn about Newton's laws or be introduced to them for the first time in like middle school, junior high, just a really basic introduction. Of course, if you've had high school physics and you've seen these before in high school physics. So hopefully this will be a little bit of a review for you. So if you could really quickly in the chat, just give me some indication of whether or not you've heard of Newton's laws of motion before. Just type like yes or no into the chat. Okay, great. I'm seeing a lot of yeses. So awesome. You guys should have a pretty good head start for today's topic then. It's okay if you don't remember the details, but I think they'll come back pretty quickly once you see the material for today. So let's roll through them. Okay, so to start off, I have this like little kind of a pre-test thing just to see what you guys know or think you know about Newton's laws and how they act in the world around us. So if you could do me a favor, grab a piece of scrap paper or something. There are 20 statements that I want you to write down if you think they are true or false. And then we'll go through the answers in just a minute. Okay, number 1, a force is required to keep an object moving in a given direction. True or false? Don't type it in the chat. Write it down on a piece of paper or something. Number 2, an object moving upward must be experiencing an upward force. True or false? Ooh, thunder. Can you guys hear the thunder in the background? That's super exciting. Anyway. Number 3, an object moving to the right must be experiencing a rightward force. Number 4, while a ball is moving upwards and rightwards towards its peak, the ball experiences a force that is directed upwards and rightwards. Number 5, if a person throws a ball, the ball experiences a force from the hand for at least a little while after the ball leaves the hand. Number 6, a cannonball is shot from a cannon at a very high speed. The force of the explosion will be experienced by the cannonball for several seconds, or at least a little while. Number 7, if an object is at rest, then there are no forces acting upon the object. Number 8, astronauts float around the International Space Station because there is no gravity in space. Number 9, objects do not weigh anything when placed in a vacuum. All right, the next set is on a different slide, so I'm going to pause here for just a second. Let me know in the chat when you're ready for the next set of questions. All right, I'm getting a couple readies done. Good, another 10 to 20 seconds. All good. Okay, so the next set of questions. Number 10, all objects weigh the same amount when placed in a vacuum, regardless of their mass. True or false? Next question. An object weighs less on the moon than it does on the Earth. Number 12, the mass of an object on the moon is the same as its mass on the Earth. Number 13, a high-speed object moving at 200 miles per hour will weigh less than the same object when it rests. Number 14, a high-speed object moving again at 200 miles per hour will possess measurably more mass than the same object when at rest. Number 15, weight is measured in pounds, mass is measured in newtons. Number 16, a free-falling object still has weight. Number 17, weight is the result of air pressure exerted upon an object. Number 18, a more massive object has more inertia than a less massive object. Number 19, fast-moving objects have more inertia than slow-moving objects. And last one, number 20, an object would have no inertia in a gravity-free environment. So again, I'll give you a couple seconds to finish writing down your answers. Give me a ready or a done or a good to go, something like that in the chat, so that I know you're good to go. All right, seeing some dones. All right, we'll give it another maybe 20 seconds for you to finish your thoughts, and then we'll go through the answers together. All right, let's do it. So on the first screen, numbers 1 through 9, all of those are false. Not one single statement of those is true. That tends to blow people's minds a little bit. I don't know if you guys got tripped up on any of those, because of course I can't really see your answers. But yeah, I think there are a lot of common misconceptions that people have, especially people who have never taken physics before. They tend to think that if an object is moving, there has to be a force that's actively pushing on it in the direction that it's moving. And that's just not true, right? Because if we think about throwing a ball up in the air, for example, um, if a force had to be acting on the object in the direction that it's moving, then you would never be able to throw a ball and have it go anywhere after it's left your hand. And of course, that doesn't happen. Like the ball doesn't just like stop as soon as our hand lets go of it. So I think, the wording of that tends to trip people up a little bit. But once you actually think through like real life scenarios of these things, then it's a little bit easier to see, right? Number 4, for example, while a ball is moving upwards and rightwards towards its peak, the ball experiences a force that is directed upwards and rightwards, not necessarily anymore, right? Initially, in order to move in that direction, it had to have a force in that direction. But the moment it leaves the hand or the baseball bat or something, it can continue that motion even though your hand is not still actively pushing it. I think another one that kind of surprises people a lot is number 7. If an object is at rest, then there are no forces acting upon the object. We'll see as we go through the slides today why that is false. But another tendency of people is to just think force causes motion. So if there's no motion, there's no force. And that's just not true, right? Number 8, astronauts float around the International Space Station because there's no gravity in space. I actually hear a lot of people say that there's no gravity in space, which is just it's not true. There is gravity in space. You cannot go anywhere where there's no gravity. And that's a really, really good thing for us. If there were no gravity in space, then there would be nothing holding the Earth in orbit around the sun, nothing holding the moon in orbit around the Earth, and everything would just be flying around somewhat chaotically. And that doesn't happen. So there's definitely gravity in space. Everyone knows gravity disappears when you stop moving. Yeah. No. Okay. The next set. There were some true ones in numbers 10 through 20. So number 11 was true. Objects weigh less on the moon than they do on Earth. That's true. The mass of an object on the moon is the same as its mass on the Earth. That's true as well. So you have to remember the difference between mass and weight. Mass is kind of the amount of stuff that is contained within an object. Whereas weight is a force. It's the force of gravity pulling down on that object because of its mass. So anything that has mass is going to experience the force of gravity. Is going to have a weight on it. But the weight is not always the same depending on where you're located. Your mass, or the stuff that's making you up, is always the same. Number 16 was true. A free-falling object still has weight. Yes, because again, weight is the same thing as the force of gravity. It's just another word for it. And we learned in chapter 2/3 that free fall is when an object is moving just due to gravity. So force of gravity is acting on it. And number 18 was true. A more massive object has more inertia than a less massive object. So we'll be talking today about inertia as well. It ties into Newton's first law. But all of those other statements are false. So how did you guys do with this, this quiz? Did anybody get them all correct? Or are there any that really surprised you? Some embarrassingly bad mistakes. Don't feel bad. It happens to everybody. Ooh, yeah, because you didn't read the full question. That would make a difference. That's a good thing to keep in mind when you're taking college classes, right? You want to make sure that you read the full question. Okay. Well, you don't have to share your score with the whole class if you don't want to. But uh, hopefully you guys can, throughout the course of today, as we talk through Newton's laws, hopefully you can see how to correct some of the misconceptions that you might have about forces and motion and mass and that sort of thing. Um, so let's get going if there are no other questions about this kind of pretest. Okay, let's move on. Okay, so here is a common misconceptions quiz. It has a bunch of questions. We're not going to go through all of the questions. I took some of them, but this is a really great resource for you. Physicsclassroom.com, excellent. I always recommend that my students check it out because it does a really good job of explaining the concepts, and it has simulations that you can try out if you're having a hard time visualizing what's happening. But they also have more of these types of questions along with the answers and explanations of the answers. So if you struggled with some of these questions today, I definitely recommend that you go to that website and check out their quiz about this. It's really good, really helpful. All right, so Sir Isaac Newton is going to be like the big man on the block today. He is a pretty important guy. If you don't know much about him, you probably still know of him because he's kind of a big deal. He lived from 1643 to 1727. And I just love this quote from him. I think it's really, really interesting to consider. If I have ever made any valuable discoveries, it has been owing more to patient attention than to any other talent. Like, that just is so interesting to think about. Um, because I'm just going to take a quick second and like run through just a quick list of 10 of his most important contributions to um, science and math and the modern world. And yet, like, even with these 10 that we'll go through, he says, if I've ever made any valuable discoveries, it's been owing more to patient attention than any other talent. And I think that's encouraging. It should be encouraging to you. Because he's saying like it wasn't because he was super talented, it's because he was attentive and patient. And anybody can be attentive and patient. So here we go. Here's our list of 10 huge contributions from Isaac Newton. First of all, 3 laws of motion that laid the foundation of classical mechanics. And these laws of motion, the ones that we'll go through today, are like so fundamental to physics that we call it Newtonian mechanics. Like this whole class of Physics 1 that we're going through is called Newtonian mechanics because it's based off of the things that he proposed. And his laws are still today an excellent approximation of motion and physical stuff at the speeds and the scales of everyday life. So his Newtonian mechanics don't apply in every situation. And we'll see, maybe we'll see if we get there. You know, some of Einstein's theories kind of, they don't replace Newtonian mechanics, but they're a little bit more specific for like higher speeds and scales that we don't interact with day to day. But for our everyday life, Newton's laws are it. Number 2, he was the first to formulate the notion of gravity as a universal force. So gravity exists everywhere in the universe, and it everything in the universe is impacted by gravity. So this idea that he proposed about this universal force of gravity helped explain tides and the trajectories of comets, which, it has farther reaches into science than just what we're going to deal with today. He published this book. Principia is the short nickname title for it. But that book is one of the most important works in the history of science. It features revolutionary new mathematical descriptions of the universe and calculus, kind of an important thing. It explained Kepler's laws of planetary motion. It validated the heliocentric model of the solar system, so the fact that the sun is the center of the solar system and not the earth. It enabled the following industrial revolution, and it's still considered the fundamental work for the whole of modern science. No big deal. He discovered the generalized binomial theorem in 1665. So he wasn't just involved with science, he was also really important in the realm of mathematics. And this generalized binomial theorem is valid for any rational exponent, and it's still used extensively in mathematics today. But he also contributed other theories in mathematics, such as Newton's identities and Newton's method for finding the minimum and maximum of a function, an easy way to find the reciprocal of a number. He also studied the power series and finite differences. There's a lot of stuff that he did in the realm of mathematics as well. He invented calculus in 1665. Again, no big deal. I'm just going to invent calculus to explain physics. I just can't. But yeah, anyway, calculus, it was the first form of analysis that was able to find the slopes and areas under curves, which, as we learned in chapter 2, is an important aspect of determining the motion of an object. He invented the first reflecting telescope in 1668. So up until this point, telescopes had been built with lenses, which are fine, but they are very large and cumbersome and expensive. The annoying thing about lenses is that you have to make sure both sides are polished very, very exactly. Otherwise, it'll skew your focal length and distort images and all that stuff. So the refracting telescopes previously, the ones that had used lenses, were just really large and difficult to use. And so he decided to do it with mirrors instead, which can shrink the size of a telescope by half easily. And they're a lot cheap, well, sometimes cheaper and easier to manufacture. He determined that white light was a mix of colors that could be separated and then recomposed using prisms. So he basically became the foundation of physical optics as well. He identified light as the source of color sensation. So he said that color is the result of objects interacting with already colored light instead of generating the color themselves. So, that's kind of an interesting thing to consider. He inferred that oblateness of Earth's spheroidal figure, that's a really hard word to say, spheroidal. But anyway, the Earth is not a perfect sphere. It's squished a little bit because it's rotating. He was also the first to analyze the phenomenon of Newton's rings, which are interference patterns created by the reflection of light between a spherical surface and an adjacent flat surface. He formulated Newton's law of cooling. So the rate of heat loss of a body is proportional to the difference in temperature between the body and its surroundings. He introduced the notion of Newtonian fluids, or fluids that have a fixed constant viscosity, even through different rates of shear, like just tons of stuff. And then he also performed the first analytical determination of the speed of sound in air. So yeah, he's kind of a big deal. He was so much of a big deal that he was the second scientist to be knighted. So he was knighted by Queen Anne in 1705. So that's in itself a huge deal. And yeah, comment there, which aided Herschel into proposing the idea of the invisible light spectrum. Yeah, so not only were his individual contributions super important and foundational for science and mathematics and the modern era, but a lot of the resulting theories and laws and discoveries were built off of him. And still he says, if I've ever made any valuable discoveries, it has been owing more to patient attention than any other talent. So there's that. But anyway, we're going to get into his 3 laws of motion without further ado. So Newton's first law of motion is also called the law of inertia. And I think a lot of people can quote the law without necessarily knowing what it means. But anyway, the law says an object at rest tends to stay at rest, and an object in motion tends to stay in motion. Most variations, I guess, of this law will leave out this part that I've included. So stay in motion in a straight line at a constant speed, unless acted upon by an unbalanced force. And I just add that part in there because I think it's really important to remember that the motion of an object is going to be in a straight line at a constant speed unless there is an unbalanced force or an outside force or an external force that's acting on that object. So basically, if we had to summarize this for a 5th grader, an object will keep doing what it was already doing unless something makes that change. So it takes a force to change the motion of an object. And down there, that last bullet point is kind of the equation for Newton's first law. We won't really refer to it very much. We won't really calculate anything with it for Newton's first law. We'll tie that more into his second law in just a couple of minutes. But that initial symbol in the equation right there is called sigma. It means the sum. You may have seen it before in your math classes. So the sum of the forces, and force there, F, is bold because it's a vector. So the sum of the forces equals 0. That means that the change in velocity over time is 0. Right? And we should hopefully remember this symbol for change in something over time, the derivative, right? The derivative of velocity is acceleration. So that will tie into Newton's second law in just a couple of minutes. But first, I think it's important to nail down what we're referring to when we talk about a force. So a force is an interaction, a push or a pull, which could cause a change in the object's movement. It doesn't have to change the motion, but it could change the motion. And there are 2 different types of forces that exist, 2 categories. The first is a contact force. So that's when 2 objects are actually touching each other. For example, your foot kicking a ball, or a table holding up a book, or my hand punching somebody's face. Yeah. So that would be a contact force. There's also field forces, which do not require the 2 objects to touch each other. They can act at a distance. So that would be like gravity or electromagnetism. The unit of force is newtons, because clearly he's a kind of a big deal. And so the symbol of a newton is a capital N, and that's equal to 1 kilogram times meter per second squared. So even just examining the unit we kind of get a hint at Newton's second law, which is, again, coming up in a couple of minutes. But it's kind of tedious to always have to say or write kilogram meter per second squared. So we just shorten that to newtons. All right, so up there I put the law again in gray just so we keep it in mind. And I underlined that last phrase in the law, the unbalanced force. Sometimes people call it an external force or an outside force. But I think unbalanced force makes the most sense, just conceptually. So only unbalanced forces change the motion of an object. These are forces that do not have an equal and opposite force, which I'll tie into his third law in just a minute. So some examples of scenarios where we can think about an unbalanced force. A soccer ball is at rest, right? It'll stay at rest, not doing anything, just chilling on the grass, unless there's an unbalanced force that acts on it. So in the picture there, an unbalanced force would be the force of the kick. And then that would change the motion of the ball. Another example, two teams are playing tug of war, pulling with equal force on the rope in opposite directions. That would not have an unbalanced force unless one of the teams starts pulling harder than the other team. And if one of the teams starts pulling harder than the other team, then that would cause a change in the motion of the group, right? So the key word here is change its motion. An object that's at rest still has forces acting on it, right? We learned that in the pre-test thing. So we just want to look at if the motion is changing, and that will lead us to understand if there's an unbalanced force. All right. So this is also called the law of inertia, but inertia is a vocab word that we need to go through as well. So inertia is the tendency of an object to resist changing its motion. Again, the key word here is change. Objects can still move and not have an unbalanced force acting on them. So it's changing its motion. It's not the tendency to resist motion, just resist change. Inertia in itself is not a force. That's another big misconception that students have a lot of the time. Inertia does not cause something to change its motion. It's an object's like internal resistance to changing its motion. So like when your mom wakes you up at 7 in the morning and tells you to go outside and mow the lawn, you probably have some internal resistance to changing your motion and getting out of bed, right? So that would be like your personal inertia, your resistance to changing your motion. All objects have inertia, and the more mass an object has, the more inertia it has, so the harder it is to change its motion. The only thing that really matters for figuring out how much inertia something has is how much mass it has. The speed that it's going does not matter for inertia. Only the mass matters for determining how much inertia something has. So for example, it's hard to make a train start moving. Like if there's a train stopped in the train station and you are behind it, pushing it, trying to make it start moving, it's very difficult for you to be able to do that. But on the flip side, once it is moving, it's really hard to make it stop. Right? So if the train were coming towards you, you would not, hopefully not, want to try to stop it yourself unless you're like Thor or Captain America, because I have just been watching the Avengers all weekend. Right? It's hard to make it stop moving because it has so much inertia, because it has so much mass. Stop it Spider-Man style. Yeah, sure. I mean, if you can do that, all power to you. On your way to school, a bug flies into your windshield. Since the bug is small, it has little inertia compared to your car, so its motion is easier to change than your car's motion. Yeah, so I don't know where you guys live, but here in Florida, there's this like stretch of road between here and the Orlando airport, where if you drive down this road, it's just guaranteed that your windshield will be covered in bug splats by the time you get to your destination. But typically those bugs are small enough that when they hit your windshield, they splat and they don't really slow you down at all, because the bug has so much less mass compared to your car. Its motion is a lot easier to change than your car's motion. And there's a comment there, the bugs in Africa will change your motion. I do not wish to see that. Man, there must be some pretty crazy bugs there in Africa. Okay. So, question then, if objects in motion tend to stay in motion, why don't moving objects keep moving forever? What do you guys think? Type your answer in the chat. If objects in motion tend to stay in motion, why don't moving objects keep moving forever? Resistant forces, air resistance and gravity, external forces like air resistance. Good. So, oh yeah, there's a good word that I was looking for. Friction, air resistance, and gravity. Friction too. Yeah, great. So we have in real life, we have these non-ideal scenarios where friction and air resistance exist. And there's almost always some unbalanced force acting on your object, like friction, gravity, air resistance, etc. Right? And so these, in the chat, somebody called it resistance forces. These are almost always present in real life. And again, typically in Physics 1, we'll be thinking about an ideal case where we're ignoring these things, but we can't ignore them in real life. Like they do exist. Right, so if you have a book sliding across the table, it'll slow down because of friction between the book and the table. That should be a ball thrown upwards, slows and falls back down because of gravity. Right, the ball doesn't continue to just go up and up and up forever, unless again you're some kind of superhero and can throw things with that much force. But it'll fall back down because gravity is an external or unbalanced force that's pulling it back down. But if we were thinking about like an ideal case in outer space, away from friction, and if we could get far enough away from other objects where gravity is minimized, then a rocket ship launched with a certain direction and speed would keep going in that direction and speed forever. Right? Again, we're assuming that it's far enough away from other objects that it wouldn't collide with another object and it wouldn't get sucked into orbit around another object. So space is sometimes taken to be like an idealized environment in that case. But we have never really, well, we just can't really experiment with that in introductory physics here. So I'm going to skip ahead to Newton's third law. We'll come back to his second law in a couple of minutes. His second law is a little bit more mathematical, I suppose, so I wanted to save that for later. But his third law is also called the law of action-reaction. And it says, for every action, there is an equal and opposite reaction. And so what I like to do there is put in parentheses force. For every action force, there's an equal and opposite reaction force. And the reason I do that is because a lot of people take that word reaction and in their minds they equate it to mean result. And that's just not true. In this law, a reaction is a force. It's not the result of pushing on something. Okay, reaction is not the same thing as result. And we'll go through a couple examples of this so that you can hopefully see the difference between those things. There is an equation that illustrates this law. The force of object A on object B equals the negative force of object B back on object A. Okay. So these forces are equal in magnitude and opposite in direction, which is why one of them is negative in that equation. Again, remember that force is a vector, the direction matters. There are some comments in the chat before I keep going. Before Newton, we could push walls like nothing. Yeah, man, Newton just had to go and ruin that. And there's a point of zero gravity between the Earth and the Moon. Surprised physics teachers haven't extorted that yet in questions. Yes, there are actually several points where where that's true. They're called the Lagrange points. There are 5 of them. There's one between the Earth and Moon. There's one behind the Moon, which is where the James Webb Space Telescope, whenever it actually launches, is going to just kind of chill there in that Lagrange point because it's a point of like stable gravity. There's one just ahead of the Earth's orbit. There's one just behind the Earth and its orbit, and there's one between the Earth and the Sun. So 5 Lagrange points. The reason why teachers haven't extorted that yet in questions is because it's pretty advanced mathematics, and you'll get there when you talk about physical mechanics and orbital mechanics, which is like physics 3. They don't call it physics 3, but physical mechanics. But if you're interested in learning about those things, they're called the Lagrange points. I'll type it in the chat here just so you can see it. Lagrange points. But yeah, that's a great comment to bring up. So back to Newton's third law. Any object can have multiple forces acting on it at once, and each one of those forces would have a reaction force associated with it. Okay, so here are some examples of Newton's third law. I don't know if any of you guys are Office fans, The Office TV show, but my husband and I love it. We've watched it, I don't know, 4 or 5 times all the way through. There are 9 seasons of it. So we just like put it on when we're doing work and it's just in the background. It's hilarious. Big fan. But anyway, Andy gets angry and punches a wall. So in this example, the interaction pair, or the pair of objects that are interacting with each other, is Andy and the wall. So the action force in this scenario is Andy's hand hits the wall. The reaction force is that the wall hits Andy's hand back. So at that moment where they're colliding with each other, Andy's hand is pushing one way, but the wall is pushing back on Andy's hand as well. And the result is terrible pain, a hole in the wall, and anger management training. What made Andy angry? There are lots of things that make Andy angry, and there are several times that he punches a hole in the wall in the show. So I'll let you go and watch it if you're interested. But you can see, hopefully you can see that the reaction and the result are not the same thing, right? A lot of people will say, oh, every action has an equal and opposite reaction. So like if I punch you, you'll get mad. I mean, yeah, but you getting mad is not the reaction force. That's the result. So here's another example. Dwight is sitting on his fitness orb. So in this example, the interaction pair is Dwight and his orb. The action force is his body pushing down on the orb. And the reaction force is the orb pushing back up on his body. It holds him up. So as a result, Dwight can sit on the ball without falling to the ground until Jim comes with scissors and removes that reaction force. Right? So Jim applied like an unbalanced force in that case, which caused a change in Dwight's motion. But up until that point, Dwight could have sat there quite happily for some time, well, forever, until until Jim gets irritated. Excuse me. So the stronger the action force is, the stronger the reaction force is, because again, they're equal in magnitude, opposite in direction. Okay, so I want you to give it a try with the following 2 scenarios. So I want you to think through what the interaction pair is, the pair of objects that are interacting with each other. the action force, the reaction force, and the result for this scenario. Michael hugs Jim. Okay, so take a second and think through the interaction pair, the action force, the reaction force, and the result in this scenario. There's a comment, he didn't hug him, he tackled him. I mean, semantics. It was an enthusiastic hug. Michael's very happy to see Jim, even though he doesn't look it. All right, so what's our interaction pair? Go ahead and type it in the chat. What's our interaction pair? Mikey and Jimbo. Yeah, great. Michael and Jim are two objects that are interacting with each other in this scenario. Good. What is the action force? Michael, be more specific though. Michael doing what? Michael tackling Jim. Yeah. Yeah, like Michael colliding with Jim, hugging him. Yeah, good. What's our reaction force? So Michael and Jim falling over would be the result. That's not the reaction force. So yeah, this does tend to be the sticky point for students a lot of the time, mixing up reaction force and result. So if the action force is Michael like colliding with Jim, then the reaction force would be Jim's body colliding with Michael's, right? Same magnitude, opposite directions as each other. The reaction force and the action force are always going to involve the interaction pair. So if Michael is hitting Jim and Jim is hitting Michael, that's our action and reaction force. The result is that then Jim falls over from the ferocity of Michael's love, excitement. I don't know. Does that make sense? Okay, let's try another one. So again, in this scenario, I want you to identify the interaction pair, the action force, the reaction force, and the result for the scenario where Dwight throws a watermelon off of the roof onto a trampoline. And I will say, there are a couple of different interaction pairs that you could choose in this scenario. So I'll give you a couple seconds to think, and then we'll go through these together. Okie dokie. So what did you guys choose as an interaction pair? Again, there are several that you could have chosen. Dwight and the watermelon. Dude Perfect and watermelon. Okay, so the two of you then are looking at like right when Dwight is throwing it off of the roof. So in that case, what is the action force? The throw. Okay, good. What is the reaction force? Be careful, remember, reaction force is not the same thing as result. Colby, I like your answer the best. The force exerted on Dwight by the melon. Right, if the action force is that Dwight is exerting a force on the melon, And the reaction is that the melon is pushing back on Dwight's hand, right? When we're thinking about these scenarios, we can only pay attention to the interaction pair. So if you're choosing the interaction pair to be Dwight and the melon, then nothing else in the scenario matters. The trampoline doesn't matter, the car doesn't matter. That's not part of your interaction pair. So if Dwight and the melon are your interaction pair, then the action force is Dwight pushing on the melon, the reaction force is the melon pushing on Dwight's hand, and the result then is that the watermelon goes flying. Yes, the reaction is just mirroring the action. That is exactly right, Ming. That is exactly right. The reaction mirrors the action force. It's the same sized force, just in the opposite direction. Yes, big brain, let's go. Okay, did anybody choose a different interaction pair in this scenario? Can it be gravity with something? Yes, it can be gravity with something. So let's think about just in chronological order through this scenario, right? So the watermelon is falling down from the building now, right? Gravity is pulling the watermelon down. So our interaction pair would be like the earth, right? Because that's what's creating the gravity. So the earth and the melon. The earth is pulling the melon down, that's the action force. The reaction force, which blows people's minds sometimes, is that the watermelon is actually pulling up on the earth with the same amount of gravity, the same amount of force. The watermelon is pulling up on the earth. Same amount of force. But how come you can't tell that the earth is actually moving up to meet the watermelon? Because of mass. Yes, the earth has a lot more mass than the watermelon does. I mean, hopefully, right? So that means that the earth has a lot more inertia than the watermelon. The earth resists changing its motion more. So it's harder to get the earth to actually like move up to meet the watermelon. But the watermelon is still pulling on the earth with the same amount of force upward that the earth is pulling the watermelon downward, right? And so the result is that the watermelon falls down. So our next interaction pair, let's say the watermelon and the trampoline, right? So the watermelon hits the trampoline, is the action force. The trampoline pushes up on the watermelon with the same amount of force. That's the reaction force. So watermelon down, trampoline up, same amount of force, opposite directions. And the result is that the watermelon springs off onto the car, right? So then in the interaction pair where it's the watermelon and the car, the action is the watermelon hits the car. The reaction force is the car hits the watermelon back. And the result is that the watermelon explodes. Okay, right. The watermelon can't handle the reaction, so it breaks. Yeah, the watermelon is just not sturdy enough to withstand that amount of force, so it breaks. Just like the wall when Andy punched it, right? The wall exerted the same amount of force on Andy's hand, but the wall wasn't rigid enough, it wasn't sturdy enough to be able to withstand that amount of force that that Andy punched with. Okay, does that make sense? Can we see like the difference between what the reaction force is versus a result? Yes, yeah, good. Okay, so on a scale of 1 to 5, how confident do you feel in your ability to take a scenario and identify an interaction pair, action force, reaction force, and result? Okay, good. I'm seeing a lot of 5s, 4.9. Good, good. Marco, I like your comment. I'm mind blown now. I understand why a rubber ball can bounce since the earth pushes it back upward. Yes, that is absolutely right. I love it, right? So the rubber ball hits the ground hits the ball back, and so the ball bounces back upward. That's exactly why a ball bounces, because of the action-reaction force happening there. Yay! Okay, good. It's looking like at least all of the people who have typed it in the chat feel pretty confident about this. So that is great. Good news. Okay, that's Newton's third law. It's pretty simple idea once you get the hang of it, but it does take a little bit of like a light bulb moment for a lot of people to get the hang of it, to figure out what exactly a reaction force is. But I liked that idea that Ming said it's the mirror of the action force. Right? It mirrors it exactly. Okay, so now on to Newton's second law. This one is also called the law of force and acceleration, hopefully for a pretty obvious reason when we get there. But this law states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. That sounds like super technical of a definition, a lot more technical than the other two sound. And so we're going to break down this definition. So inversely proportional means that two variables affect each other in opposite ways. So if one is increasing, the other one decreases. Whereas when something is directly proportional, that means that they affect each other the same way. So if one increases, the other one also increases. And in this definition, we have both of those relationships happening at the same time. So what's basically happening here, if we could summarize this for a fifth grader, is the more mass an object has, the more force it requires to change its motion. And so we have three variables, three parts acting in this definition, right? We have acceleration, we have net force, and we have mass. So down there at the bottom, I have the three most common ways to write this law. The first one is based on the definition. So acceleration equals net force over mass, right? And since we saw in the definition that acceleration is directly proportional to net force, that means that net force is in the top of the fraction. Whereas since acceleration is inversely proportional to its mass, that means mass is in the bottom of the fraction. But I think the more common way that you'll see it and hear it is F equals ma. A lot of people will like throw that out off the top of their heads if they want to sound like super smart at a party or something. F equals ma, E equals mc squared. But F equals ma is itself a little bit misleading, I think, because it's not just force equals mass times acceleration. It's net force equals mass times acceleration. And another way to think about net force is the unbalanced force. And I have a whole slide like just devoted to net force, so we'll get there in a minute. But the third way that you might see this written down is the sum of the forces equals mass times acceleration. And that one's a little tricky to think about too, because we can't just take all of the forces, all of the magnitudes and add them together. We have to remember that force is a vector, so the directions matter, and any forces that are left or down are considered negative. So when we add a negative number, we're actually subtracting. Okay, so when we say the sum of the forces, keep in mind that some of those forces are negative. Okay, but we'll get there in a little bit. Okay, but some examples of Newton's second law. Okay, you and your friend are racing shopping carts at the store, because who doesn't do that when they go to Walmart? Yours weighs 10 newtons and your friend's weighs 20 newtons. So if you are both pushing with the same force, whose cart will go faster? Type it in the chat. Your cart weighs 10 newtons, your friend's cart weighs 20 newtons. If you're pushing with the same amount of force, whose will go faster? Try to visualize this scenario. Colby says mine because I'm the best. Mine because Gabriel is slow. Ooh, burn. I don't know, maybe when you guys get here, you can go to Walmart and give it a try. But anyway, yeah, yours, whoever you happen to be, yours will go faster because it weighs less, right? So here is kind of like a visualization using that equation. Two foreigners caught racing in Walmart. I like it. Yeah, anyway, here's the equation. And so I tried to mess around with the sizes of the variables to illustrate what is happening in the scenario. Okay, so you're pushing with the same force. Force is the same size in both equations. Your cart has a smaller mass, a smaller weight, and your friend's cart has a bigger mass, which corresponds to a bigger weight. So the variables change the sizes there. But now, in order for the force to be the same size, if one has a smaller mass, that must mean it has a bigger acceleration. And if one has a big mass, that means it has to have a smaller acceleration. Just mathematically, that's how it has to happen. So I tried to help visualize that with the equations. Hopefully that makes sense. And hopefully when you guys get here in the fall, you can go to Walmart and see this drag race in real life. Okay, follow-up question on that though. If you are neck and neck, who is pushing harder, you or your friend? Right, Colby, your friend is pushing harder. Okay. Ooh. Anyway, yeah, again, here's our visualization of what's happening with our scenarios, our variables. Right, so there's your small mass, large, well, the accelerations are the same size in those two equations, but that gives you kind of a smallish force versus your friend who has a big mass, same acceleration, leads to a bigger force, right? So your friend has to push their cart harder because it weighs more. Hopefully that just kind of naturally makes sense to you based on your life experience. Okay, so here we're going to create a like a table of the most common forces that you will see in Physics 1. There are, of course, more forces than what we'll put in this table, but they are not as relevant for Physics 1. Things like electricity and magnetism, you won't see those until Physics 2, really, so I left those out of this table. Okay, so we're going to go through the name of the force, the symbol, the definition, the direction, the type, and the equation. And we'll be using these forces along with these equations and symbols and everything over the next couple of days as we do things like free body diagrams and all that. So I recommend that you take a screenshot or something of this table so that you have the information that you need as we go through the following problems. Anyway, our first force, and I put it first because it will apply in nearly every scenario. And I say nearly every, but I'm pretty confident it will be every scenario. And that's the force of gravity. It's also called weight, right? They are the same thing. Weight and the force of gravity are the same thing. So when somebody asks, hey, how much do you weigh? They're asking, how much does the earth pull down on you? With what amount of gravity does the earth pull down on you? So it has a couple of different symbols that you might see. It might be capital W for weight, FG or Fgrav, any of those are possibilities. So this force is due to the gravitational attraction between two objects. Usually it will be between the Earth and some object. Could be between the Earth and the Sun, or two planets, or you and a textbook or whatever. It doesn't, any two objects. If we're talking about the Earth, which is, the most common object that we'll be talking about, then the direction of it is straight down towards the center of Earth. But if it's like you and the person next to you, then the direction would be, in the direction of the two objects, connecting those two objects together. It is a field force because the Earth doesn't have to be touching you in order to still exert gravity on you. And the equation for that is force of gravity equals mass times our acceleration due to gravity. Force equals mass times acceleration, right? We know our acceleration due to gravity is 9.8 meters per second squared because we talked about that last week. So F equals mg. Okay. The next force is called the normal force, or sometimes the support force. So that gets the symbol N, Fn, or F norm. And be careful here, because remember, what is the unit of force? What is the unit of force? Newtons, that's right. And what is the symbol that we give that unit? Yeah, big N, capital N, right. And you can see here, the symbol that we often give normal force is another capital N. So just be really careful because we have two different things that are using the same symbol. Sometimes to mean normal force, sometimes to mean newtons, which is the unit of force. So it can be a little bit confusing. Typically, I like to write it as Fn for that reason. But sometimes you'll see it as capital N. It just depends. The definition, it's exerted by a surface on an object, and it is perpendicular to and away from the surface. So a normal force, normal in this case doesn't mean like common or usual. Normal actually means perpendicular. Like in a mathematical sense, the word normal means perpendicular. So that's why we call it the normal force, is because this force acts perpendicular to a surface. So if you're thinking about a table and you have like your textbook sitting on your table, perpendicular to your table would be pointing straight up, right? So it's that support force, the table pushing back up on your book, that's the normal force. And since the two objects need to be touching for that to happen, it's a contact force. So this force will be equal to the weight in any scenario where we're dealing with a horizontal surface. But if we have a scenario where we're at an angle, then the normal force, like perpendicular to this surface, would be like pointing out like this, which is not straight up anymore, right? That's also at an angle. Gravity is still pulling straight down, but now your normal force is off at a weird angle. So in that case, we would have to use our trig functions to determine the components of our normal force. And we'll go through some examples of both cases starting tomorrow. There's a question here. How can we calculate the acceleration that acts on two objects due to gravity, assuming that the objects are in space with no outside forces acting on them? We would observe its motion. So remember, acceleration is how the velocity of an object changes. So if we're talking about two asteroids, for example, in space, that are gravitationally attracted to each other, they would be moving towards each other. And so we would be able to measure, based on a reference point, we would be able to measure how their velocity is changing as they get closer. And so we'd be able to figure out the force of gravity from that. There's another equation that we'll see maybe later this week if we can get there, that relates the force of gravity to masses of objects that are not on Earth. So that's F equals big M, little m times capital G over r squared, the distance between them squared. And like I said, we'll look at that in more detail later this week. Good question though. Question, if I leave a metal bottle on a table, will the table, for a long time, will the table break and why? I guess it would depend on your table and how heavy your metal bottle is. A wooden table. I suppose if you wait long enough, that would be like years and years and years and years. Entropy is my answer for that. Okay. Another common force that you'll see in Physics 1 is friction. So sometimes we'll write that as lowercase f, sometimes ff, and sometimes f brick. So this is the force that opposes the sliding motion between two objects. This would act parallel to the surface, but opposite the direction that it's sliding. It is a contact force because the two objects have to actually be touching in order for friction to oppose the motion. And I really like this equation. I think it's the most fun equation in all of physics. Hey. But the way that you calculate friction is friction equals mu, that weird U symbol is a Greek letter mu, mu, times the normal force. Right, so mu, the coefficient of friction, it tells us how slippery the surface is. It's just a number between 0 and 1 usually. There are no units associated with it, but it tells you how slippery it is. So the smaller the coefficient, the more slippery it is. Like ice has a mu value a lot closer to 0, whereas like carpet has a much higher mu value. Okay, but yeah, it's the most fun equation. Tension force is another common one. We write that as capital T or Ft or F10s. But this is anytime you have a situation involving a rope, a wire, a string, pulling on something. The direction of it is away from the object, but parallel to the rope. So like if we have a box here, ooh, look, I have a hair tie. Say this is a box and I have this string attached to it and I'm pulling it. The direction of tension would be that way, parallel to the string and away from the object. It's a contact force because the string has to actually be attached to the object in order to pull on it. But there's not really a standard equation associated with it. It will depend on the scenario. Air resistance is another one, also called drag. So the symbol of it is Fd for drag or Fair for air resistance. It's basically another kind of friction, but it's just specifically due to wind. It acts, again, like friction, opposite to the direction of motion. It's a contact force, and there's not an equation that we will use for it in Physics 1. There are equations for it, but not that we will use in Physics 1. Any other push or pull in this scenario would be considered an applied force because you're applying a force on the object. So we just call that FA, and it would be based on the scenario. Like it would tell you you're pushing a box to the right. So then, of course, your applied force would point to the right. It's a contact force usually because, again, magnetism and electricity are physics 2. And there's no equation given for it. It would just depend on the scenario. And last but not least, there's net force, which we already talked about is the sum, well, the vector sum of all of the forces. And it would point in whichever direction is unbalanced. So the equation for that is F1 plus F2 plus ... but according to their directions. Okay, so net force, just really quickly, this will be the last thing that we get through today. The net force is the vector sum of all the forces. Vector sum just means add them together, but remember, some of them are negative because of their direction. And so another way to think about the net force is whatever amount of unbalanced force is kind of left over. So for example, if we're playing tug of war and your team pulls to the right with 100 newtons of force and the other team pulls left with 60 newtons of force, which team would win and by how much? Well, clearly your team would win because you're pulling harder, and you're pulling harder by 40 newtons to the right. So that 40 newtons right is your net force. Anytime we're thinking through these scenarios of multiple forces acting on an object at the same time, you can always ask yourself, if this were tug of war, which direction would win and by how much? And in thinking through it like that, you're actually calculating the net force. Madeline, I will go back in just a moment to that slide so you can take a picture. If the net force on an object is 0, then all of the forces are balanced and the object is in equilibrium. So that would be if the amount of force pushing left equals the amount of force pushing right, and the force pushing up equals the force pushing down. If that's true, then your object is in equilibrium. But this could happen even when the object is moving, if the object is moving at a constant velocity. Right? So this ties back to Newton's first law, right? An object in motion will remain in motion at a constant speed in the same direction unless there's an unbalanced force acting on it. If there's no unbalanced force, no net force, it can still move at a constant speed in a given direction. Right? An object in motion stays in motion. But clearly this could also happen if the object is at rest. So unbalanced forces or a non-zero net force will cause a change in the motion of the object or an acceleration. Okay, so tomorrow we will go through how to apply these laws in different scenarios. And I'll teach you guys how to draw free body diagrams, which if you took Physics 1, you probably saw and did them in Physics 1. If not, then you'll see how to do them tomorrow. But do you guys have any questions, comments, concerns about Newton's 3 laws of motion? All good? Okay, great. Well, hopefully this was a good review for you guys. I know you said, everybody who said it in the chat, said they had seen Newton's laws before. So hopefully this helped just kind of refresh it in our minds as we go forward from here. But if you do have any questions, then feel free to hang out after I stop the recording. Otherwise, I hope you guys have a great day, and I will see you tomorrow.